given by Csaba, Biro, who will talk about representing interval orders. Please.
Thank you. Thank you very much. Thank you for the opportunity to speak in this prestigious seminar. So this talk is going to consist of mostly three parts. The first part, and it's chronologically correct. So the first part I've done with my PhD student, Sida Wan. He actually went to work in the industry after graduating, but now I think next year he's back in the academia. He's going to go to and work for a university in China. I don't think, last time we talked, he didn't decide which one. He had a couple of offers there. And Andrei Kezdy is one of my colleagues here at the University of Louisville. He was on Sida's PhD committee, and he got interested in some of the problems that we were working on. So we started to work on something similar, and that's the second project. And then finally, Caroline Boone is my current graduate student, who I got interested in interval orders, and in particular, semi-orders. So I'm going to try to balance this talk. I have too many slides. I don't think I can go through all of them. So I will probably just jump through a few, which is okay, because if the talk is recorded, whoever watches it can pause, right? And they can still read it. So let's see if I can turn the page. Yes. So probably we all know this, but let's just go through this to be on the same page. A poset is a set with a reflexive, antisymmetric, and a transitive relation. The relation we call a partial order, and the partial order together with the set is called a poset. That's short for partially ordered set. A poset is a chain. It could be a subposet of a poset if every pair of elements are comparable. And we can also say that the poset is a total order, or sometimes we call it a linear order. For me, they all mean the same thing. It's an anti-chain if no two elements are comparable. And the maximum size of a chain in a poset is called the height of the poset. It's usually denoted by h of p, but that differs from author to author. And WP is the width of the poset, is the maximum size of an anti-chain in the poset. So what are interval orders? Interval orders is a special class of posets. And first, we will define interval representation for posets. It's a function from the ground set. This ground set, that was the set on which the partial order is defined on. This function is from this set to a set of closed intervals of the real line. And we call it an interval representation if it is true that for two comparable elements of the poset, let's say x and y, x is less than y, implies back and forth. So it implies, and being implied by the fact that f of x, which is an interval, is entirely left of f of y. So basically, we're mapping the poset into intervals in a way that the order of the intervals is representing the poset. And because this is an if and only if, it also means that if two elements are incomparable, that the intervals must be overlapping. So a poset is an interval order if it has an interval representation. Not every poset has an interval representation. In fact, this poset that we sometimes call 2 plus 2 is just two incomparable chains of size 2 each. It's not an interval order. This is not hard to see. One can just try to draw the intervals. You have to draw A, and B has to be entirely right of A. And now you're trying to find an interval for C, which overlaps both A and B, because it's incomparable to them. And because D has to be right of C, it will be right of A, no matter what you do. It can't overlap both A and B. In fact, it can't overlap A once you chose an interval for C. If this is not clear, just sit down with a piece of paper and pencil, and you will get it in no time. So the interesting thing is this classical theorem of Fishburne that states that this is a characterization of interval orders. If a poset does not have a 2 plus 2 as a subposet, it is an interval order. And I'm going to show you a proof, which is not, I'm not going to show you the whole proof of this, but I show you the idea of a proof that's not due to Fishburne. So this idea, well, this idea of the proof is due to Greenlaw, who was Kenneth Bogart's student. And in his PhD thesis, he introduced this proof. It's a very beautiful one. So I give you the idea. So first of all, we start with an element of the poset X, and we take every element which is less than that element. That's called the down set of X, and we denote it by D of X. And the upset of X is the set of elements that are greater than X, and we denote it by U of X. I use this script D to denote the set of all down sets for every element of the poset, and the script U for all the upsets. Now, it might be tempting to think that the cardinality of the script D is the same as the size of the ground set of the poset, but it's not true, because you can have multiple elements who have that have the same down set. So you can have significantly fewer down sets than elements in a poset. In fact, if you look at all the minimal elements of a poset, for example, the down set of all of those are empty. So here is a simple claim. This could be given as an exercise in a class to show that these three are equivalent. The first one is that the set of down sets is totally ordered by inclusion. The second one is the set of upsets is totally ordered by inclusion. And the third statement is that the poset has no 2 plus 2. So we can start with the poset that has no 2 plus 2, and we want to prove that it's an interval order. So what do? We can actually prove, and this is not so simple, that the number of down sets is the same as the number of upsets. One can find a bijection, but that's not trivial. And also you can probably prove this by induction. And now that we know this, we can order them, right? Order the down sets in an increasing order by inclusion, and order the upsets backwards, so decreasing order by inclusion. I write here that D1 is the empty set because the empty set is always a down set, and it's also always an upset. I didn't mention, but in this whole talk, I'm going to assume that every poset is finite. So there's a minimal element whose down set is empty, and there's a maximal element whose upset is empty. And so therefore the empty set is always there in this list, in the beginning or at the end. And so what I want to do here is I want to show that this poset has an interval representation, right? So I will show you how to find an interval for every element. So we pick an element, and then we find a down set of that element and the upset of that element on this list. It's somewhere there, right? Find that index. So we find the index of the down set, let's say that's I. We find the upset of the index, let's say that's J, and we're going to assign this interval ij to the element A. Now, it's totally not trivial that this works. It's not even trivial that this is a correct interval. I mean, who knows? Maybe theoretically J could be less than I, right? But it works. And this is the proof that I'm not going to show you why it works. So this is a representation that uses integer endpoints from 1 to n. M is called the magnitude of the poset. And it uses the least possible number of endpoints of all representations. And it's also called sometimes the canonical representation of the poset. So here's an example. Let's say we want to find the interval for A. And what we look at is we look at the down set of A, that is CF and G. So we find CF and G on the list of down sets. It has index 3, and the upset is just E. So we find E on the list of upsets, that is index 4. So 3, 4 will be assigned to A. Notice that we have another interval here, J, that gets 3, 4. And why is that? Well, it's because J has the same upset and the same downset as A. They're very similar elements. They call duplicated holdings, and they have some importance in some of the work that we've done here. Actually, it's quite important in most of these. they can be represented by the same interval. So this interval representation is not a bijection in this case, but that's okay. Okay, so what is a semi-order? An interval order is a semi-order if it has a representation with every interval of the same length. And we can take that length to be 1, because it doesn't really matter. Now, here's a theorem. An interval order is a semi-order if and only if it has no 3 plus 1 subposet. So what's a 3 plus 1? A 3 plus 1 is a 3-element chain and 1 extra element that's not comparable to any of the elements in the 3-element chain. This theorem, again, just like the previous one with the 2 plus 2, one direction is easy. 3 plus 1 is not semi-order. If you try to do a representation, you can try to cheat like I did on this picture. It almost looks like I succeeded, but the middle interval on the top line is a little shorter. So they're not all the same length. And it's pretty easy to see why 3 plus 1 cannot ever be represented with intervals of the same length. The other direction is not so trivial. It's to prove that if a poset does not have a 3 plus 1, then there is a representation with unit intervals. Let me emphasize that this representation is not necessarily and typically not the canonical representation of the poset, right? This poset is still an interval order. It has a canonical representation. It probably won't happen with unit intervals. Okay, so a linear order is a linear extension of the poset P if it's a chain and it's an extension of P. So that's a pretty simple thing, right? We just extend the poset until all the incomparabilities are gone. And the set, if you take a set of linear extensions, we call it a realizer if their intersection is the poset P. So what does this mean? It means that, well, first of all, if you have two elements in the poset, x and y, and x is less than y in the poset, then x is going to be less than y in every linear extension, right? So that's going to appear in the intersection, no question. That's really it's not deep at all. Now, if you want to construct a realizer, the tricky part is to make sure that incomparable elements of P do not appear in this intersection. So that means that if you have two incomparable elements, x and y, you have to have a linear extension in which x is less than y, and you have to have one in which x is greater than y. And in this way, in the intersection, neither relation is going to be there. And so that's how you make a realizer. So a natural question arises, is it true that every poset has a realizer? This is pretty trivial for finite posets, because if you take the set of all linear extensions, you will have, for every incomparable elements, you will have a linear extension which orders them in either way. So the set of all linear extensions is always a realizer. So now the challenge is to find a realizer which is small. It does not have a lot of linear extensions. And once you found it, the minimum cardinality of a realizer is called the dimension of P. So I'm saying all of this because the first couple of results are mostly about dimension of interval orders that have certain properties in their representations. So a couple of basic facts. If P is a chain, you can represent it with a single linear extension. In fact, it has one linear extension. And so that's a very trivial statement, and of course, and it's vice versa. If P is an anti-chain, then the dimension is 2, because you order the elements in one way, and then you just reverse the ordering completely, and these two linear orders are going to be they are going to form a realizer. This is not true. The converse is not true here. So the dimension is n of this particular poset. This is just to illustrate that one can find large dimensional posets. This is a poset when you have its height 2. So you have upper elements and lower elements, and the lower elements are all comparable to the upper elements, except for the one that is directly across from them. These are part of the n-dimensional hypercube. They're subposets of the n-dimensional hypercube. So the n-dimensional hypercube is in fact of dimension is at least n. In fact, it is dimension n. So all these notions of dimensions that we think are somehow coinciding here. I'm cheating a little bit here because embeddability in hypercubes is not exactly the same as dimension. It's not the same, but that's okay. All right. So the name is explained by this fact that the dimension of a poset is the least positive integer for which p can be embedded into r to the t. R to the t is the t tuples of real numbers, and here the ordering is just the coordinate-wise ordering. And if the ordering is contradictory somewhere, then the 2 points are incomparable. Okay, so here's an observation. Interval orders do not have these posets Sn, not even for n equals 2, because 2 plus 2 is, if I go back here, this poset is full of 2 plus 2s, right? A1, B2, and I don't know, A2, B5, I think. Yep, they form 2 plus 2s. So even just for n greater than or equal to 2, for n equals 2, Sn is in fact a 2 plus 2 itself. So these are not interval orders. So the question, natural question arises, are there large dimensional interval orders? And the answer is yes. If you take the interval order In, which we can define to be this interval order, when you just take the positive integers from 1 to n and take every interval that appears on those, then the dimension of this interval order as n goes to infinity converges to infinity. More is known here. In fact, this problem of dimension of this interval order is very well studied. And we know that the dimension of this interval order is of the order of log n. I'm not going to show. I have some slides about the proof why this goes to infinity without doing anything heavy calculations, just relying on Ramsey's theorem. I think that's a very pretty proof, but I would definitely run out of time if I did it. So I'm just going to go through it quickly, and if you want to read it, you can just pause the video. So here is the full proof, and I'm going on. Okay, so we look at the semi-orders. The dimension of semi-orders is at most 3. That's another theorem. This is a theorem of Rabinovich, and I'm gonna tell you roughly what the proof is. It can be done really nicely. We take a ranking partition of the poset into antichains. That means that you take the set of minimum elements of the poset, minimal elements of the poset, and that's A1, and now you remove them. And now you take the set of minimal elements of the poset again, that is A2, remove them, and just do it repeatedly. This is what we call a ranking partition. So once you do that, it's not hard to prove that if you have, say, A1 and A3, every element in A3 is going to be greater than every element in A1. So if they are 2 apart, they are going to be totally comparable. So now we can group together, and this is not only for A1, A3, but A2, A4, A3, A5, and so on. So now we can group together. We can group together the odd indexed sets. We will call that A sub odd, the union of them. And then we take the union of the even ordered sets. We call that A sub even. And then we construct 3 linear extensions. First, we're going to put A even over A odd. Now, you can't just say introduce every relation there, because some elements maybe are already comparable. But all I'm saying is that if an element in A even is incomparable to an element in A odd, then in the first linear extension, I'm going to put A even, or the A even element over the A odd element. And I'm going to do that for the second linear extension backwards. And this basically kills every incomparability except inside of the antichains. So I can make a third linear extension in which I can destroy the comparabilities within these anti-chains. And from here, once you know this, to actually finish out the details is not that hard. Okay, so now after all of this warm-up and everything, let's talk a little bit about mostly the first part of this new research, and this is restricted classes. So let's take a set of non-negative real numbers. We will say we define the S representation of a poset to be an interval representation in which every interval is of length of one of these numbers. Okay, so we can restrict it in any way we want. We can say, I want every interval to be either length 2 or length 7. And that's a bracket 2, 7 bracket representation. So the class of C of S is going to be the set of posets that have an S representation. And some shortcuts here, C of AB will be the set of posets that have a representation in which every interval is of length between A and B. And we will say C of A is the class of posets in which that have a representation with every interval is of length between 1 and A. And we will use OC instead of C if both open and closed intervals are allowed. So another definition of poset is called K-count. I noticed this typo earlier and I didn't fix it. Oh, if it is in, no, there is no typo. I think I did fix it. A poset is K-count if it is in CS for some S having K elements. So this means that one can represent this poset with K different interval length. And ICP is going to be the minimum K for which P is K-count. It's called the interval count of the poset. So what are the interval count 1 posets? Posets with interval count 1. So looking at the definition, this means that these posets have a representation in which every interval is of the same length. Well, these are exactly the semi-orders. Okay, so what about 2? What are the posets that can be represented with 2 different lengths? Well, we don't have a nice theorem for this. We don't have a nice characterization. We don't even know how hard it is to determine algorithmically if this is true about a poset. This is not known to be NP complete, or it's not known to be polynomial. It's just not known. So one interesting fact here is that if we're hoping for a nice characterization like we had before, when we could just forbid some set of minimal subposets, then that's hopeless. If we take at least K at least 2, then there is no forbidden family of minimal subposets, and this was proven by Fishburne. And there is a nice survey paper on the interval count of posets and graphs, and this survey paper has this sentence in it. This is by Sergio Oliveira and Schwarzfitter. If you Google their name and survey paper for interval count, I'm sure you find a paper. They write this in the paper. The interval count problem is an intriguing problem in which very intuitive statements are proved not to hold. And I did learn this the hard way. We conjectured many statements that turned out to be false. So when we started to work on this problem with Sida, he was reading this paper of Keller, Trenk, and Young, and this appeared in Graphs and Combinatorics. And they proved that if P is in OC1, so that this means that every interval is of length 1, but you can use open and closed intervals as well, then the dimension is still less than or equal to 3. So this is a generalization of Rabinovich's theorem. And they also proved another theorem in their paper in which they say if you are only using interval length 1 and length 0, the dimension is still less than or equal to 3. So they asked a couple of questions at the end of their paper. They said, can you find a good upper bound for for CRS, where R and S are just two positive length, two positive numbers. And they offered something that they came up with, but they asked, can you improve on this? And in general, they did the same thing for K-count posets. And they also asked this question of how many interval lengths do we need to take to make a four-dimensional poset. So Sida, as a good graduate student, sat down and answered all three of the questions. Well, he improved the bounds on the first two, and then he didn't immediately answer number three. Really, I have to say, Andre Kezdy answered number three, but it didn't go into that paper. So the first theorem that we did was this: if the interval count is at most k, then the dimension of the poset is at most 2 times log k plus 3. And for k equals 2, this gives 5. So what do we know about k equals 2 now, after this theorem? So we know it is at most 5-dimensional, and we know that it is at least 3-dimensional because we have actually semi-orders that are of dimension 3. We do know that the Rabinovich bound is sharp. So we knew it was either 3 or 4 or 5. Which one it is? Which one is the best bound? It's not clear. So we tried to find a 4-dimensional 2-count poset, but we couldn't. But Andre Kezdy, who was, as I mentioned, was on his PhD committee, he got interested, and he implemented some state-of-the-art dimension finding algorithm that was much better than the one that we used. And he ran a computer search, and he found the poset. He found the 2-count poset that was 4-dimensional, and that one has 45 points and irreducible, meaning you remove any point from that poset, it's going to be 3-dimensional. So it's hard for me to believe that you need 45 points, but maybe, I don't know. So now we know basically that the best bound here for k equals 2 is either 4 or 5. We don't know which one. And here's another theorem that we proved, and this is for interval. So remember, CT means that the interval length from 1 to t are allowed, any number from 1 to t. So now you allow infinitely many lengths, but they are still restricted. The maximum length is restricted here. And so we proved here that you have a 2 times log t bound from above. And a couple of notes here. For t equals 2, this gives 4, but we actually couldn't find a 4-dimensional poset in C2. So still again, this question is open if there is one. If every interval is of length 1 except for 1, then we could prove that that's not enough to increase the dimension over 3. And also note that this is the best possible in terms of rate of growth, because what I mentioned, the interval orders that we called IN a long time ago at the beginning of the talk, so that was about 25 minutes ago, I mentioned that the dimension of that is asymptotic to log n. So this means that at least in terms of rate of growth, and that poset is in CT, if you're using I sub t is in CT. So that poset is of dimension log n. So this means that this rate of growth is best possible, but the constant could be improved. We don't know if that 2 is right or not. Okay, so this paper actually is still under review, and I think it's been at least a year that we submitted it. So if the referee is in the audience, can you please referee it? All right, so let's go on, and then let's switch gears a little bit. And I want to talk about now the research that was inspired by this paper. And we did it with Andre Kezdy and Jeno Lehel. So one approach to try to find an interval representation of a poset is to turn it into a linear programming problem. So this is just an overview of what a linear programming problem is. This is one standard way of phrasing a problem. You have a set of linear inequalities, which is this ax less than or equal to b. And you know that the vector x is non-negative, so every component of the vector is non-negative. And you are trying to maximize C transpose x, which is really just a linear function of the variables of the variable vector x, you try to maximize that subject to these two conditions. The good thing about linear programming that we have lots of theory and lots of tools. Linear programming problems are polynomially solvable. And the bad news is that even if all the entries here are integer, the optimal solution may not be an integer. And if you want the optimal solution to be an integer, then it turns into what we call an integer programming problem. And that one is hard, unfortunately. But still, there are lots of theory and tools, so that is true. So let's turn the interval representation problem into a linear programming problem. So the goal here is to, you're given a poset and you try to find a representation. So let's define three variables for each element of the poset. We're going to call these Lx, Rx, and ρx, and they're going to represent the left endpoint, the right endpoint, and the length of the interval for x. And so now I can write down all the conditions that are required for these variables to represent an interval representation, or to construct an interval representation for the poset P. For each element x, I require that the length of that interval is going to have to be the distance of the right endpoint and the left endpoint. That's a linear equation. If you're not familiar with linear programming very much and you're wondering, oh, you just wrote an equation, not an inequality, it's not a problem, right? I can replace an equation with two inequalities when I write both sides, or both directions. So this is still a linear programming problem. Ρx has to be non-negative. I certainly can make Rx and Lx to be non-negative. That's not a problem in the requirements. Even if these requirements are not made, it's still an equivalent formulation of a linear programming problem. All the tools can be used. Now, for each pair of two elements, x and y, that's my second requirement here, I guess. I have this requirement that the right endpoint of x has to be left of the left endpoint of y. This is what's forcing the ordering of the intervals. And finally, for incomparable elements, I basically force them to be not comparable. So I will say the left endpoint of y has to be beyond the right endpoint of x. If you are worried that this could make y less than x, that's true, but in reality, x and y are symmetric here. So if x is incomparable to y, then y is also incomparable to x. So you will also have the symmetric inequality in your system. So that's really all we need. And now, if we find variables like this, it's going to give us a representation. What's the problem here? This is still not a linear programming problem because it has a strict inequality. Strict inequalities are hard to handle. Yeah, so the solution set of a linear programming problem always gives a closed polyhedron in an n-dimensional space. And this is not closed because of the strict inequality. So we can fix it in a way. It's not a perfect fix, but it's going to work for us. And we're going to require that any two intervals are of distance of comparable elements are of distance at least one from each other. And so this way I can turn that strict inequality into a non-strict inequality by requiring that the left endpoint of my larger interval is at least one beyond the right endpoint of my smaller interval. This way I do get a convex polyhedron in 3Rn. Every point of this polyhedron is actually a representation of the poset, and every integer representation of my poset is a point, because every integer representation does satisfy this requirement that two comparable elements are separated by at least unit length. So this is something that we can work with. We can detect easily if P is an interval order, because now we just have to figure out if this polyhedron is non-empty. If you're worried about, again, the fact that this does not contain every representation, it's not really a big deal because every interval order does have an integer representation. This is not hard to see. If you want to detect that P is a semi-order, we can do that still by requiring that every two interval is of the same length. That just gives us a bunch of more equations. We can't really say, first, I wrote that here rho x has to be equal to 1 for each x, but that's actually not correct, because now the fact, if I'm requiring that the distance of two intervals that are comparable is at least 1, that I can't simultaneously require that every interval is of unit length. However, I can require that they are of the same length. And you can add an arbitrary objective function here to optimize this representation. So that's kind of nice too. So Andre originally, Andre Kezdy, got interested in the 2-count problem or the k-count problem. So we thought maybe we could take the projection of this polyhedron to forget all the left and right endpoints and just focus on the length. And if we understand this length polyhedron that we called Q, again, all this is just a projection of the polyhedron into these coordinates that represent the length. If we could understand this better, then maybe we could figure out if the, say, just the 2-count or the k-count problem is polynomial or not. That's one major question here. And so we started to study this, and we actually didn't solve the problem. So it's going to be still an unsolved question at the end. Maybe that's not so unusual, but we found very, very beautiful things. So that's good. For example, we realized that Q is an affine convex cone, and it has a single vertex, and this single vertex corresponds to the canonical representation. Turns out that we were not the first who proved it. Doyen and Powers proved the same thing fairly recently. We found their paper later, but we did it in a different way, and that was nice because we could prove other things too. And this has a corollary. Every positive linear functional is minimized at the canonical representation. So I'm going to give you a little more details here. So first, a few definitions. A conic combination of vectors is just a set of linear combinations where all the coefficients are non-negative. Sometimes this is called conical combination. I'm not really sure grammatically which one would be more correct, but I call this conic combination. And the convex cone is a subset of Rn that is closed under conic combinations. An affine convex cone is just a convex cone that's shifted away from the origin, because a convex cone would have its vertex at the origin, right? That's not necessarily true here. And so an affine convex cone is just a convex cone that's shifted away. A ray is a vector that has this property that if you start that vector from V0, which is the vertex of the cone, and then you just add the multiple of that vector, that ray, to this vector, then you stay inside of C for all non-negative T. And an extreme ray is a ray that cannot be written as a conic combination of rays in an untrivial way. So on this picture on the left, R1 and R2 are two extreme rays, and any conic combination of R1 and R2 is in fact a ray. So there's a representation theorem that's a very old theorem, I think, of polyhedra, which says that if you have a convex polyhedron that's described this way, it's a set of linear inequalities with non-negative variables. So this is how we actually defined a linear programming problem. We optimize over these vectors. Then this convex polyhedron can always be written as a sum of two other sets, and in these two sets, P is a bounded convex polyhedron and C is a convex cone. So in our case, P is trivial. For the length polyhedron, P consists of a single vector, and that single vector is that length vector of that canonical representation. So let me see. I think I'm going to skip this because I want to have time for the end. But I want to make a note here at the end, which is a corollary of what we've done here. it's actually a very simple corollary, but I found it interesting and counterintuitive. So here's a task. Let's suppose you're given a poset, given an interval order, and you have to find this representation. But every vertex of this interval order has a price. Maybe you have a golden point and you have a steel point. The golden point is a lot more expensive than the steel point. How is this reflected? Well, when you construct this representation, you have to pay for every interval. And for the golden point, you have to pay a lot more for the interval per unit than for the steel point. So you probably want to choose a short interval for the golden points, so you don't have to pay so much for that. And maybe as a consequence, you don't mind increasing the length of the steel steel point, right? So the interval of the steel point. Well, it turns out you can't really do much. No matter what the price of each point is, the optimal representation is always the canonical representation. So that will always, you can't really play around here. You create the canonical representation, and then the adversary changes the prices around on the points. The optimal will still remain the canonical representation. This is all a consequence of what we've done. It's just a very simple consequence. It's not even the deepest one. Not even very deep, to be honest. Once we prove all these theorems. But I think that's interesting. Okay. Yeah. So here are some of the details of what we've done. I think I'm going to skip this as well. Yes. So what we wanted to do is we wanted to find, okay, so we understand that this length polyhedron is an affine convex cone. We understand what the vertex is. But if we really want to understand this convex cone, we want to understand maybe the extreme rays. We somehow want to be able to generate this cone, right, in an efficient manner. So we try to find the extreme rays of Q. And we found something interesting, and I'm going to skip the details, but what we found is that all these extreme rays are binary, meaning that, well, yeah, so when I say all the extreme rays, of course, if you have an extreme ray, a constant multiple of that is also an extreme ray. But what I want to say is that the extreme rays can be taken as binary, meaning that every coordinate is going to be either 0 or one of those. And we also have a set of rays among which we can find the extreme rays. Unfortunately, the set is too large to be useful, but it's still kind of interesting to understand what happens here. This paper is being written at the moment, so I can't give you a reference for the details yet, but hopefully it's going to be finished in a couple of weeks, I think now. Maybe in a couple of months at least. It's a very long paper, so it takes some work. So, okay, so the extreme rays are binary, and we kind of have a way to find them. We can't find them themselves. We can find a big superset of them. The big superset is too large, and it's not so easy to figure out what's a minimal, what is the word, generating set of them. So here's another way to try to describe this cone. One can find a Hilbert basis. What's a Hilbert basis? A Hilbert basis is a set of, well, so you have a convex cone, and a set of vectors form a Hilbert generator set if every integer vector in this convex cone can be written as an integer conic combination of vectors of H. So conic combination means that the coefficients must be non-negative, and now they have to be also integer, okay? So that's a Hilbert generator of a cone. It's not even obvious that this always exists, but it does, and the proof is actually not even hard. It's beautiful too. So a minimal Hilbert generator of a convex cone is called a Hilbert basis. And if you have a pointed convex cone, this just means that the vector and its opposite cannot be in the cone together unless it's the 0 vector. Then C has a unique Hilbert basis. This is another theorem. This is less easy than the previous one, but it's also not too hard. This is all something that has been known for a long time. And what we can do now really well and quite efficiently is to compute a Hilbert generator set, actually a Hilbert basis for our length polyhedron. Because we can find a large Hilbert generating set, we call those fundamental extenders, and we have a good algorithm to find which one has to be chosen for the basis. This relies on some theory that actually requires this generator set, the intersection graph of this generator set, to be a perfect graph. So it's crazy, but we actually use the perfect graph theorem to prove this. And so this gives rise to an efficient algorithm to find a Hilbert basis, and this algorithm is polynomial if the poset is bounded with. The details are formidable, yes. Extreme arrays, we don't really have a good way of computing them, no efficient way. But here is the crazy thing. Computational evidence shows that the set of extreme arrays is the Hilbert basis. I think for every poset we tried, this was true. I don't know why it should be true. I can't prove it for sure. So anyway, that's super interesting. Maybe there is a large poset for which it's not true. Okay, so let me skip this and let me spend a couple of minutes on, well, okay, so I'm just going to mention some open problems here. This did not really help us to get closer to solving the K-count problem. So it's still a big open question is, how hard is it to determine if a poset is K-count? What's the time complexity? Do we have an elegant characterization? Or maybe even just nice conditions for the K-count problem? Okay, and so let me spend the last couple of minutes on this last section. So a new graduate student, Caroline Boone, came along, and she was interested in these problems. So I gave her something to read, and she's very good at programming. So she started to generate random semi-orders to play around on the computer. And so one time we were talking about it, and I said, so how do you generate these semi-orders? And she said, I'm just picking n uniform random points on an interval, 0L, and then for each of those points, I construct a unit interval whose left endpoint is that point, and that will give us some kind of semi-order. And I was like, I don't like that, because you're certainly not getting anything near uniform distribution on the set of semi-orders on endpoints this way, right? This is kind of, this is quite clear, because if you take a fixed point, a fixed number n, and you generate these points, and now you take a super large L, super long interval, almost certainly your poset is going to be just a chain, right? Because the points will be far from each other. So no two intervals will overlap. And if I take a very, very tiny interval, maybe 0, 1, just so that we're a little crazy here or something, or 0 epsilon, then it's virtually certain that you're getting an anti-chain, right? So what happens here is that when you let that go to infinity, the number of, or the probability of each semi-order you're getting is converging to 0, but the probability of chain converges to 1. Okay, that was accepted, but she was still hoping, I think, that maybe we could get a sweet spot for L where something nice happens. So this is how the problem was born. How fast are these probabilities going to 0? And so with a little poset theory and a little probability theory, we actually figured out how to compute the probability of every semi-order. And there's a theorem here. I don't state the theorem because it's kind of technical, but basically you're computing an integral here. So I just gave an example here. Here is an example of a poset on 6 points, and this integral is what computes the probability. Now, maybe this is scary, and you say, what does this guy talk about an integral at the combinatoric seminar, right? Okay, forgive me for this, but look at this integral. This is not actually hard to compute. First of all, what we're integrating here is a constant function. You can even factor that out, right? So we're just it's really a volume computation in n dimensions. It's not really an integral. And then if you actually want to compute it, what happens here, and I didn't tell you what the theorem is, but these lower bounds and upper bounds of the integrals are always just either the variable or the variable plus one of the variable or one of the variable plus one, or it's 0 or it's L, which at the end means that this computation will integrate a polynomial in every step. When you're integrating it from inside out, you always have a polynomial. So you can write a computer program that easily computes this. That's not really a big deal. It's really an algorithmic way to compute it. Now, why it works, that requires a proof. But then again, once you know it works, it's actually not hard to compute it. All right, so that's okay. Now we can compute it. But what we really would like to see is maybe tell what this probability is, or maybe just say if two posets have the same probability of going to 0, or maybe asymptotically the same probability going to 0, based on some kind of combinatorial properties of the poset. That's what a combinatorialist wants to do, right? So we found some interesting things. If you have first let me give you a definition here. This is general for posets. If you have k posets and you take the disjoint union of the ground sets of these, so making sure that ground sets are disjoint, you can construct a new poset by basically placing them on top of each other. So you're going to put down P1, you copy P1, and then you copy P2 over P1, and you make every element of P2 greater than every element of P1. And then you copy P3 over the whole thing, and you make every element there greater than every element before. This is a construction that's called a lexicographic sum of these posets over a chain. And if a poset cannot be decomposed into not in a non-trivial way into a lexicographic sum, then we call it a brick. So a brick, the only decomposition a brick has when it's just one single poset itself, right? K equals 1. So first of all, we know that the probability of a brick is going to be asymptotic to c times 1 over c times L to the 1 minus n for some constant. And this is basically saying that if I go back to that integral there for a second, because here we're dividing by 1 over L to the n at the beginning, this means that after that division, this is a linear function of L. So that's one theorem. And another theorem is that once you know the probabilities or the asymptotics for the bricks exactly, we can actually tell what the asymptotics of the poset is. So these are the two main things that are proven so far. This is also work in progress. The main question here is what is the constant for the bricks? Can we link it to a combinatorial property of the semi-order in some interesting way? We do have some partial results on this. So we already know for certain posets how to get that that coefficient, and we have also some conjectures. And another question, which kind of what instigated this whole research is how does the semi-ordered polyhedron look like? Now the length polyhedron is trivial, right? Because it's just going to be actually it might not even be that trivial, because I wanted to say it's just a single point 1 1 1 1 1. But that's not true, actually, because if we're taking the representation polyhedron, there are other ways of representing clearly a semi-order, not only with the unit interval length. So all these polyhedra are interesting questions for semi-orders. And I think that's it. Thank you.
Thank you very much. Very interesting talk. And definitely a lot of possible questions. There's still a lot of work in progress, which is really nice. So maybe we go into question session. Anyone wants to ask a question?
I have a question. There are a lot of posets associated with convex polyhedra of different kinds, bounded convex polyhedra. Do you have results about when you can represent those kinds of posets, or?
So are you, if I understand this question correctly, maybe you're talking about, say, containment orders of
No, you start with
posets?
convex polytope of some sort and look at it.
Oh.
There are various partial orders you can associate.
Right.
The kind of thing Gil Kalai and others have studied.
Yeah, we did not study those because those are typically not interval orders.
Oh,
And
you
so,
can prove they aren't, you mean?
yes.
Okay, okay.
Yeah, I mean, you do get a bunch of 2 plus 2s in them typically. Like if you're talking about the one that's when you take a convex polytope and then you define the relation if one face is contained in another, for example.
Yeah, that kind of
thing. Yeah, those are typically not interval orders. I hope I'm not wrong about this, but anyway, we did not study them.
Okay. Thank you.
Yeah, I had a similar question because from the beginning of your talk, like when you gave the definition of the order, I thought, oh yeah, Fishburne actually was involved into a different study, right, of interval orders. I mean, there's not interval orders then, but it's a containment order, right? So where you kind of mapping poset into set of intervals, and the relation is only one, like x smaller than y. You can only interval corresponding to x is contained inside interval contained, like interval corresponding to y, right? So it's a different order
it's very
compared
different
to what
yes.
you have. But
it's very different.
Yes.
And yeah, sorry.
Yeah, the thing is that if, say, intervals overlap, then in both cases it's incomparable elements, right? But you have a case where one is a subset of the other, they will be still incomparable, right? In your order. While in that other order, where you have completely x smaller than y when you actually compare them, it will be incomparable in that case, right? So they, in a sense, they're almost dual to each other, I would say, right? So you're kind of going from what you call comparable in one case to incomparable in another. And so from that point, it might be that if you just take any poset and now take a dual of it, right? So somewhat dual, so whatever was comparable becomes incomparable and vice versa, right? But
yeah, that's an interesting thing you say. So let me say I have many thoughts about this. So one of them is first of all, the interval orders by containment are exactly the posets of dimension at most 2.
Yes, that's correct. Yes, that's
that's of course a very different class, because as we talked about it, interval orders in this way that I define them are going to be unbounded in dimension, and in some sense the class is much richer for these kind of interval orders. Another thing I must recommend, I can't help but I have to recommend my PhD thesis because a big portion of that was studying segment orders, and there are 2 kinds of segment orders, and one of them would be in one way generalization of interval orders, and another one would be in one way generalizations of interval containment orders, and the 2 generalizations became very similar. In fact, I don't think anyone ever proved, I'm certainly not me, but I don't think it was proven that the 2 classes are in fact distinct. So that's an interesting comment. And the third is that I don't think there is an obvious or easy way to take kind of like the dual of a poset. When we say the dual of a poset, we always just say that we reverse the relation, but incomparability remains incomparability, and comparability mirror. So the comparability graph is the same. It's not like in graphs when you can just take a complement. So it's interesting. I don't know how you would get like the opposite of a poset, because when you order elements in a chain or an anti-chain, you want an anti-chain to become a chain. There are basically k factorial number of ways to do that when there are k elements in that anti-chain. So, and some of them you might not be able to finish, right? So this is not clear how to do that.
Yeah, I agree. I mean, that's just a thought like coming after like your definition. So I had only time till end of your talk to think through that. And
Yeah,
yeah,
of course, yes.
But like my initial question was like, is there any relation to the, but you already answered to that, right? So that's
Okay.
not like really two different classes. And so like it's not much intersection that you could get
Right.
from
Yeah, it's
one
very small
study into
intersection, yeah.
another.
Yeah, the intersection is just the two-dimensional interval orders, right? Or interval orders of dimension +2, which are, yeah, it's not, it doesn't even contain semi-orders.
Mm-hmm. All right.
I see that somebody put a question in the chat. I don't know.
No, I think it's someone just left because
okay.
to go.
Okay. Yes.
More questions? All right. If no more questions, then let's thank the speaker again. If there is a referee, we need to hurry up, right? And refereeing the paper so you'll get it out quickly.
Thank you very much.